half power beamwidth and what is called beamwidth between the first two nulls. Okay, so let us see. This is from this point to this point. This is called half power beamwidth, and from this point to this point, it is called beamwidth between the first two nulls. It is because these two are the null directions. So we are taking the beamwidth between the first two null directions. That is called beamwidth between the first two nulls. So you know already that what is called null direction. The direction is the direction in which there is no radiated power is called null direction. That means in this direction there is no radiated power. In this direction also there is no radiated power. So therefore this is the first null direction on the right side, and this is the first null direction on the left side. So therefore between these two, we are taking the beam width in terms of degrees or radians. Therefore this is called first null beam width. And similarly, these two are the half power points. Since we are taking the beam width between these two half power points, this is called half power beam width. It is in shortcut can represented by HPBW. So we'll take the example how to calculate the half power beam width. So let us see here radiation intensity is given for an antenna. So that is u of theta equal to cos square theta. So these two are the variation of the azimuthal plane and elevation plane. And in order to calculate the half power beam width, the radiation intensity must be made equal to 1/2, because the power must be equal to half. So therefore 1/2. So therefore cos square theta is made equal to 1/2. So therefore we are getting that theta value as pi by 4. Okay. On the left side, pi by 4, this is pi by 4. On the right side also, it is symmetrical. Therefore, it is pi by 4 and pi by 4. Okay. The total beam width is equal to pi by 4 plus pi by 4. Therefore, that is equal to 90 degrees. So, 90 degrees in the radians can be represented by pi by 2. And what is called FNBW. So, you know already that FNBW is half that of the, is approximately half that of the half power beam width. Yeah, this half power beam width is half that of the FNBW. So likewise also you can calculate. Or otherwise, in order to take the null direction, what is null direction? So null direction is direction in which there is no radiated power. So therefore this cos square theta can be made equal to 0. So in that way also you can calculate. So there you can get that u of theta is made equal to 0. Therefore theta is coming about pi by 2. In that way you can also calculate. So this type of problems are generally seen in the unit 1, and a lot of problems are there in the unit 1 material that is already sent to you. You can go through that. If any doubt, you can call me also. And this is the directivity. So already it is defined. What is directivity? It is nothing but the ratio of the radiation intensity in a given direction to the average radiation intensity. The expression is radiation intensity is given by u of theta comma phi divided by average radiation intensity. So average radiation intensity is generally the radiated power divided by 4 pi. So therefore radiated power divided by 4 pi. That means PRAD divided by 4 pi in the denominator. So that the 4 pi will be coming to the numerator. So therefore 4 pi into U by PRAD. So relation between directivity and half power beam width. So the generally this beam width is generally measured in two planes. One is in the horizontal plane and one is in the vertical plane. In the horizontal plane, if you measure, this is phi of HP. This is theta of HP. HP means half power beam width. So it is because the radiation pattern is a three-dimensional graph. So therefore, the beam width can be measured in two planes. One is azimuthal plane, and the another beam width in the elevation plane. So here this is half power beam width measured in the azimuthal plane, half power beam width measured in the elevation plane. So therefore, for smaller antennas, generally this uh, directivity and half power beamwidth can be related through this expression. So if you see, this entire one can be replaced by beam solid angle, that is gamma A. So this theta hp into theta hp into phi hp will become beam solid angle gamma A. So therefore, D is inversely proportional to this gamma A. That means if beam solid angle is more, automatic directivity is less. Or otherwise, if you see, these two are nothing but the beam widths. That means if beam width is more, the directivity is less. If beam width is high, the directivity is low. So in that way, you can observe also. So next derivative again, it is nothing but the ratio of the power density in a given direction for an antenna divided by the average power density in the direction. So relation between gain and the gain and the directivity. So gain in the sense power gain. So the power gain is represented by GP and directive gain is represented by GD. If antenna is 100% efficient, both are equal. That means theta A will become 1. So if a antenna is not of 100% efficiency, these two are related by this expression. Okay. The maximum directive gain is called directivity. The maximum directive gain is also called directivity. Sometimes this GD is replaced by directivity. So that if that is the case, that GP is equal to eta A into directivity of the antenna. Some cases we see that also. That means this GD is replaced by the directivity. It is because the maximum directive gain is nothing but the directivity. So the directivity and effective aperture both are related in this way here. Let us see. Uh, if lambda is constant, that means if the frequency of the radiation is constant, automatically directivity and effective aperture both are proportional to each other. This is FRISS formula. It gives the amount of received power from the transmitting antenna. So in this expression, these are nothing but the gains of the transmitting antennas and receiving antennas. Otherwise, these might also be called as directivity of the transmitting antenna and directivity of the receiving antenna. And PR and E is nothing but the power received by the receiving antenna. PT is the power transmitted by the transmitting antenna. So R is the distance between the two antennas. Lambda is nothing but the wavelength corresponding to the electromagnetic radiation. So here this is transmitting antenna and this is receiving antenna. The power is transmitted from transmitting antenna to receiving antenna. This is effective area and directivity. Both are related like this. So, and ultimately this FRISS formula can be represented like this. So FRISS is the name of the scientist, therefore it is called FRISS formula. Front to back ratio, it is nothing but the ratio of radiated power in the front direction to the back direction of the antenna. That means the front power radiation divided by back power radiation. So it is also represented in decibels. So antenna polarization, there are generally the types of polarizations are linear, circular and elliptical. So beam efficiency, so here this definition it is written like this, and the solid angle subtended by the main beam to the sum of the solid angles subtended by all the lobes. So otherwise it can also be stated like this. That is area of the main beam divided by the total area of the pattern. Like that also it can be defined. That means entirely this is with respect to the main beam. So therefore it is represented as omega capital M. So next one is stray factor. So it is represented as the sum of the solid angles subtended by the minor lobes. So the sum of the solid angles subtended by all lobes. So it is with reference to the minor beam. Therefore, this is called omega small m omega a. Otherwise, it can also be stated as the area of the minor beam to the area of the total area of the pattern. Effective height or effective length. So it is nothing but the ratio of the voltage received at the antenna terminals by an incident wave of electric field strength E. So therefore H equal to V by E. So this can be defined for transmitting antenna and also for receiving antenna. That means transmitting antenna effective length and similarly receiving antenna effective length. Both are similar and both are same. For an antenna, the effective lengths are same and it is acting as transmitting antenna, and if the same antenna is utilized for receiving antenna, the effective length is also same from the reciprocity theorem. That means effective length of transmitting antenna is equal to effective length of the receiving antenna. So already you know the single wire radiation, how single wire is acting as a radiator. Okay, so normally if the wire is bent or truncated or terminated, then only it is able to radiate. Otherwise, it is not able to radiate. That we have seen. It is two-way radiation. That means as long as the wire is straight, there is no radiation. If the wire is tapered at the other end, then only it is able to radiate. It is because as long as the wire is straight, the top wire radiation cancelled by the bottom wire radiation. So as the wire is tapered at the other end, automatically there will be net radiation. That net radiation shown in the this figure.